Hello everyone, my name is Eugene Kang and this is Lab 2, Projectile Motion for Physics 2211. So the purpose for this lab is to demonstrate Newton's second law by studying the motion of an object following a projectile trajectory with experimental and computational models under various conditions, with those conditions being the existence of a drag force or not. So for this experiment, I'll be observing the motion of a paper ball being thrown with an initial x velocity, then I'll be observing that motion using a software called Tracker. Then after that, I'll create a computational model using GlowScript to predict the trajectory of the ball that first takes into account only the gravitational force acting on the ball, and then when there is a drag force applied onto the ball. The results of this experiment were that the computational drag model closely resembled the data of the observed model. So before we go on to analyze the data we collected, it's important to define Newton's second law. This law states that the net force acting on an object is equal to its change in momentum divided by a certain time period. That means if the net force on an object is zero, then its change in velocity is also zero. Using these three equations from Newton's second law, we can combine these into an equation known as the velocity update formula, shown here. Then, using the velocity update formula, we can derive this equation known as the position update formula, which will then calculate the change in position of an object over a certain time period, given its average velocity. The procedure for the lab is as follows. First, we define the system as the paper ball, and then define the earth and the air as the surroundings. Next, we have to measure the mass of the ball. Then, we record a video of the ball undergoing projectile motion. After that, we use Tracker to measure the ball's relative x and y positions over a time interval. And then, using that data, we code a computational model of the ball's motion, assuming only gravity using GlowScript and the code template for this lab. Then after that, we code another computational model that takes into account the drag force along with the gravitational force. After that, we plot the data of all models onto a single chart, and then we compare their x and y positions or their trajectories. After that, we compare all the models and conclude if the ball's trajectory follows Newton's second law of motion. So here's the video uploaded into Tracker. As you can see, we can use this software to pinpoint the ball's position for each frame in the video. And then we also measure the length of a portion of this meter stick right here, so that we know the relative distances within the video. Using this software, we get a chart of data points on the bottom right and a graph right here that shows us the relative positions and the calculated velocity of the ball at each frame in the video. So using these data points we got from Tracker, we can plot them on a chart to see the ball's trajectory right here. Then we can compare the results of the computation models to this line and see how accurate they are. So here's our code for the computational model, which only takes into account the gravitational force acting on the paper ball by the Earth. Using our initial velocity and position values we get from Tracker, along with our measured mass of the paper ball, we can input these values into our code, which will output another set of data points of position, which we can then compare to the observed data points. As you can see here, we input each measurement on each line of code, with delta t being 0.033 seconds, because that's the amount of time that passes between each frame of the video. And then the coefficient for the drag force B is going to be equal to 0, because we're not taking that into consideration yet. Then F net is the ball's mass times the acceleration of gravity. And then these two lines, 82 and 83, are our velocity update and position update formulas. So now that we've ran the script, we can now compare both of the data point line trends. As you can see, the computational model seems to overshoot the x distance for all points in time, since it doesn't take into account the drag force pushing against the motion of the ball. So in order to create a more accurate computational model, we should consider the drag force acting on the ball, which is going to slow it down. So we're going to revisit our code again, but this time we change the coefficient b to some number, compare it to the line of the observed data points, and then retweak the number to see if we can get a closer approximation until we're as accurate as can be. The equation for the drag force here at line 80 represents that the direction of the drag force will always be negative to the direction of the ball's velocity, and that it will always have a magnitude of the ball speed squared. Through this method, we arrive at a drag coefficient with a value of 0.016. So now that we've taken into account the drag force, let's compare all three sets of data points. As you can see here, the second computational model does a much better job at approximating the trajectory of the observed paper ball, sticking closer to the blue line than the orange line does and being very similar to the observed trajectory. This tells us that the second computational model gives us evidence that Newton's second law is true. So even though we saw that the computational model accounting for drag and the observed data points were really similar, we saw that they weren't exact. This difference could be for a couple of reasons, the first being human error. It's essentially impossible for a person to throw an object that's exactly parallel to the surface of the ground, meaning that our ball's velocity may have had a small y component to it. Human error could have also caused imprecise tracking of the ball's center of mass, skewing the data and altering the final data points and trajectory path we got. The second source of error comes from rounding errors. The numbers that GlowScript gave us were rounded to a certain decimal point, meaning that the numbers we put into the chart are slightly different from their true values. But now that we've done the lab and gotten the result, we can now ask a further question. What if the ball had been thrown straight up with the same starting speed? Would it take longer to reach the floor? The answer to this question is yes, and we can prove it using our computational model. So I went into the code and changed the initial velocity to be straight up with the same magnitude, and as you can see, the ball that is thrown across hits the ground at approximately 0.4 seconds, while the ball that was thrown straight up is still 0.65 meters above the ground, even a little past 0.4 seconds. This shows that it takes a larger time span to reach the ground if the ball is being thrown straight up compared to if it was being thrown parallel to the ground. That was the end of this lab report. Thank you for your attention.